Hi there, welcome to DesignSpark Tech Tales with Worth Electronic. Today we've got Sebastian and Maria from Worth Electronic, and we're going to be talking about shielding and thermal management. Hi guys, would you like to say hello to DesignSpark?
Yeah, absolutely. Hi everyone. I'm Sebastian. I've been a product manager at Würth Electronic for a little over 6 years now. My main tasks are taking care of the heat spreading products or the graphite solutions from the thermal management side, and then of course helping and supporting users with their thermal designs.
Fantastic.
Maria, now it's
Hi
your turn.
everybody. Hi everybody. I'm Maria. I'm also in Würth Electronic, but not for 6 years. And now it's almost 2 years and a half, something like that. First, I was more involved in the shielding development my first 2 years, and now I'm more going to the field of simulating and giving this support also to our customers.
Fantastic. Well, it's great to have you guys on the call today. And I think this is an area where we can see a lot of synergy. You know, if we're talking about shielding and thermal management, they're very reliant on each other in terms of bringing together good design. So I'm really looking forward to this conversation, and I know we're going to be talking about some of the products that you guys offer onto the market. Maria, if I start with you, the product we're really here to talk about today is really the EMI patch shielding. So can you just tell me a little bit more about that product, for example?
Yeah, to put a little bit in context to everybody, at the end in our portfolio, what we have are products that help in the electromagnetic noise management. No, so we can have electric fields, we can have magnetic fields, and we have different components or different products that help to suppress that noise from different sources. The magic or the good thing about MI Patch, a really quite new product that we have, is that we can combine the suppression of electric noise and also magnetic noise, because we combine a thin layer of aluminum or conductive material, and at the same time this material has also magnetic absorber. So it's performing really, really well, and also in a really wide range of frequency. That is also a hot topic when talking about shielding. So this is a little bit the magic of this product.
Fantastic. And Sebastian, so from your side, we're talking about obviously thermal management. Why is it that thermal management is so important when it comes to electronics?
Well, you know, when we're talking about electronic design, what we're basically doing is we're managing energy. Electrical energy, thermal energy, it's all energy. So although we do use electrical energy or current, voltage, and so on in our devices to power them and to use them for signal acquisition and so on, what is also there is the thermal energy. And this is something that in the past it used to be not that much of an issue because components were really big. They were on their PCB. They were completely exposed to air convection. I always like to think about those old computers that instead of just being a box, they were a whole room, totally cooled with air conditioning or with just simple open windows at the beginning. And now things are getting much smaller and
Yeah.
they're getting packed together and they're going to have a higher power density. And of course, that needs to be taken care of because then you're coming into risk of component degradation, mechanical failures, and so on.
Yeah. Yeah, it's those kind of physical attributes as well, which obviously bring down the performance. And much like a human, you know, we don't tend to operate too well in extreme heat or extreme conditions, and it's
Exactly.
exactly the same for electronics. So yeah, that's a really kind of good comparison I like to make sometimes. You know, if we're feeling hot, you know, and we don't operate, then electronics is exactly the same. I just
Exactly the same.
I'm really interested to, as we talk, understand more about both of these areas a little bit more from Worth Electronics' point of view. So, if we talk about, first of all, Maria, we'll go back to the EMI shielding. Tell me a little bit more about the composition of that material. So, for example, what's the difference when we compare it to traditional absorber sheets?
Yeah, basically, the idea or the way of applying this material is pretty similar to an absorber sheet, because at the end it's a really thin material, pretty flexible, pretty easy to just stick. It's like a patch. This is why we call it EMI patch, because maybe you have already designed your PCB and you are having some electromagnetic noise that you cannot redesign and you need to accomplish some requirements. So basically, the main topic I would say is like EMI patch can be used when ferrite absorber sheets can be used also. But if we want to, for example, absorb a specific frequency, the noise of magnetic source, then we can use ferrite absorber sheet or EMI patch, depending on the shielding effectiveness you need, also depending on their size, depending on the application itself, but both of them can be used. But if we focus on electric field, we cannot use ferrite absorber sheets because these are made of magnetic materials. These are made for magnetic fields. So in electric fields, we have shielding cabinets that are basically like a Faraday cage, and this is what normally the user were using. But for these products, you need to include it in the layout of the PCB. You need to take into account from the early beginning and just have in mind that this electric field can appear. With MI patch, the advantage is that you can apply it just like a patch. You have this aluminum or conductive field included in the material, and then you can also use it in these electric fields that you may have issues without having to take into account for the earliest stage of the design. Obviously, we always recommend that shielding has to be taken into account from the early beginning, that MI patch is a really good option, and obviously, if you are in a hurry at the end of your design, it's going to perform really, really good, but this doesn't mean that you don't have to take into account from the earliest stage from avoiding any issue in the future.
Yeah, great, fantastic. Now, there's a couple of things, obviously, in terms of the applications, if we're talking about those. So, for example, in terms of the classic cabinet shielding, providing similar levels of effectiveness, what can you tell me about the things like EMC noise suppression, magnetic decoupling, and then also there's a couple of ones that I'm really interested to hear a little bit more of. But if you could answer those ones first, that would be great.
Yeah, basically, the performance, talking about shielding effectiveness of the MI patch, for example, and the shielding cabinets are pretty similar, which is a really good topic because at the end, the shielding cabinets can behave like a perfect Faraday cage. So, having a material that performs really similar to this, and it's that easy to just put the absorber sheet or the MI patch and it's working similar, it's a pretty good option. And regarding magnetic decoupling, we have a demo in which we show how magnetic decoupling works from different thicknesses, from different sizes of the material. But we really want to make a point here, and that is that sometimes we say, okay, we see a graphic and we say, okay, this is the shielding effectiveness at this frequency for this material always. Shielding doesn't work like that. Shielding is about how your setup is placed. It's really good to have a reference design. It's really good to compare performances between materials, in this case, for example, MI patch and shielding cabinets, and to have a overview in which frequencies I can use the product. This is really good, but we have to always take into account that depending on your application, depending on the distance, depending on a lot of things, you are going to need to actually test or at least simulate your device and see how it's going to work.
Yeah, absolutely. Yeah. The other ones which are really kind of interesting as well is the SAR reduction. Can you just explain what that means in terms of like the RF exposure, for example?
Yeah, mainly when we are talking about shielding effectiveness, we can be talking about different things because maybe you are in a situation in which what you want to do is absorb this magnetic field you are creating. Then you put a ferrite absorber sheet and you can measure, for example, inside and outside your cabinet, how much is the field that is arriving to your test device. So in this sense, you can say, okay, this is the shielding effectiveness I'm having with this product inside this enclosure. But maybe the issue is not that. The issue is I'm inside a shielding cabinet and I'm having, for example, reflection inside my cabinet. Then maybe I have to check of the reflection loss, or I have to check which material I'm including inside that is affecting the performance of my device inside the cabinet. So this is why we have different measurement setups. We have an application note talking about insertion loss, magnetic decoupling, and how these parameters or this way of measuring can tell us, okay, this material absorbs at this frequency, but reflects at this other frequency, the magnetic, and we can play with the field in this sense. For example, ferrite absorber sheet normally are used to absorb the magnetic noise, and normally FSFS, that are other products that we have, normally we use to redirect the magnetic field. Does that mean that they cannot use, depending on the frequency, with other purpose? Yes, of course, but these are the main applications or objectives from these different materials.
Yeah, that also makes a lot of sense, in terms of the material selection, the testing as you move through, and the spatial distance within cabinets as well. Plus, all of the other things that will interfere with that design all has to be taken into consideration. The other one I just want to talk a point is, how do we avoid cabinet resonances, for example? And could you just explain what that is?
Yeah, that's a good topic. That was my final thesis project, so really good to talk about it. Basically, when you are having a cabinet, doesn't matter if it's a shielding cabinet that are really small or maybe a whole aluminum box, you are having a conductive element surrounding your PCB. And probably you are generating at a specific frequency some noise that are interfering or are, reflecting inside your cabinet. So there are formulas to calculate when this shielding cavity resonance is going to happen, and basically a cavity resonance is an internal noise that you are having inside your cabinet due to a peak of a magnetic field at some point, or maybe you are reducing the performance of your antenna because it's not matching, or depending on the application, you will have one issue or the other one. But the main topic is I'm having at certain frequency a peak of noise.
Mm-hmm.
First, I have to find in which frequency I have in this peak of noise. If this peak of noise going to affect me, for example, the shielding cabinet, sometimes the peak of noise is at 7, 8, 10 gigahertz. Maybe my application is not working in this high frequency range, so it's not going to be an issue. But now that we are moving into higher and higher frequency, probably you are going to have a potential internal resonance. So what you can do, you can try to include a ferrite absorber sheet to absorb this noise. You can try to include EMI patch that is also working in the absorbing this material. Which material should we use? You have to test it probably, because it matters the size of the cabinet, it matters how much material I am including in it. Obviously, normally the more material the better, but sometimes we have to take into account also the expensive of this material. So we have to optimize where we should place it. And lastly, the thickness. Normally we say the thickness, the higher, the better for absorbing, but the material can also collapse, can also saturate.
Mm-hmm.
So yeah, these small tips can help us, but eventually seeing which the frequency ratings our products works, seeing where my cavity resonance is going to appear, then we will need to include one of these materials. We will work soon in an application note about this topic, because we already have made a study for our shielding cabinets and the performance of the different ferrite absorber sheets inside the cabinet for absorbing this resonance. So it's clearly an important topic for shielding.
Yeah. So there's a lot to unpack there, but really in terms of the design capabilities, you're mentioning all of those considerations that you need to make within that cabinet design, and then obviously a lot of the thought process between the EMI patch has gone into that kind of design process that engineers are going to be faced with. One of the things that engineers are also faced with regarding not just shielding, Sebastian, if I bring you back into the conversation, is the actual thermal management. In terms of where the technology is going, there's more miniaturization than ever before. So tell me a little bit more about kind of like what's on trend and the current electronics designed when it comes to more compact designs.
Yeah, absolutely. I think the tendency to miniaturize it comes from obviously the consumer market. Everyone wants more compact designs, lighter designs. Also from the shipping of equipment point of view, we live in a globalized world where we are designing something in one phase of the world and then we're shipping it to the other side to sell it. So definitely miniaturization is something that designers are challenging, and this is what I see every day today when I'm supporting also other designers. How do we challenge this increase in power density? Like I was mentioning before, components used to be big; they were able to dissipate that excess heat energy to the ambient. But now we have another factor, which is the PCB. Now most of the heat is traveling into the PCB and then it's distributing around in your PCB and then finally it's getting transmitted to the ambient. So now our PCB has gone from being a simple interconnection and holding mechanically THT components. Now it's become a part of active in an active part in thermal management, and that comes with some challenges, and those challenges are the power density. We have now to get rid of more heat in a smaller area, and we have components which are much closer together, and this is what we always discuss in the team and also with Maria, that from the thermal point of view we want the heat sources to be as far away as possible in our PCBs, but then of course from the EMC point of view or the EMI point of view, you want them to be as closer together so that you don't have all these issues. So again, like in everything, it comes with a challenge, and you just have to manage it, and that's why of course we have now much more standard techniques and the importance of proper PCB layout of components. Where are your heat sources? How close are they? How can I separate them? And then how can I get that heat out from there?
Yeah, and I think obviously you were talking about power density, heat generation, and it really is apparent, that if you look at within, say, a small enclosure, for example, the differences in the heat gradations between one part of that enclosure to the other is really kind of vast. In terms of managing that thermal heat, that in itself is a characteristic of the design that you need to consider. From a person such as yourself who is doing this, are there any kind of tips or hints that you would say about thinking about the overall design when it comes to thermal management, particularly as we do want things to be more powerful but more compact, as you said, particularly in that consumer market?
Yeah, absolutely. And this also links to EMC. The earlier you tackle these kind of issues in your design, even before the layout, the more cost effective it's going to be. Same from the EMC point of view, same from the thermal point of view. Even before you put a component on your layout, you really have to think, okay, how much power is this component going to dissipate? All my components, how are they going to be enclosed? The earlier you take care of that, the more cost effective you're going to be.
Yeah. And you were talking earlier about some heat spreaders. Are there any particular products that you want to call out within that?
Yeah, absolutely. And this is something also that we've got a fairly broad range of thermal interface material right now. We have the traditional elastomeric silicon gap fillers, but we do have also synthetic graphite heat spreaders, the WE-TGS, and it's something that in my 6 years of being here at Burt Electronic, I've seen more and more interest. And I think this is related to the conversation we just had about miniaturization. These materials are characteristic of having a really high thermal conductivity in the in-plane axis. And when we're talking about transferring energy to the ambient, what matters the most is the contact area with the ambient. The bigger the area is, the more energy we're able to transfer to the ambient, and that's why heat sinks exist. Heat sinks pack a really big area in a really small footprint. So heat spreaders are a really trendy topic right now, because first of all, the alternatives that they have are aluminum, which has a thermal conductivity of 237 watts per meter Kelvin. Fairly light, but then we also have copper, which is more expensive and fairly heavier, which has a higher thermal conductivity, around 400 something watts per meter Kelvin. And then when we talk about the graphite in the in-plane axis, we're talking about 1,800 watts per meter Kelvin. And it's very light, it's very flexible, it's adhesive on one side, and you can use it as a sticker to spread the heat over a larger surface. And the cool thing is that it can be used to enhance other materials. So let's say that my design is a handheld device and it's made out of ABS plastic. And of course, plastic has a really low thermal conductivity. So if I interface my heat sources with the housing, I'm only able to dissipate as much energy to the ambient. But by using a heat spreader stuck to the inside, even though, yes, it does have a really low thermal conductivity, I can spread the heat over a larger area and just make the maximum out of it. Also, I've come across designers who are updating their devices and they're using steel housing. Steel also has a really low thermal conductivity, painted steel, around 50 watts per meter Kelvin. So when they update their designs, their electronic designs inside, and they're relying on the same housing for passive cooling, they come into a pickle where, oh, now my temperature of my components is much higher than what I designed it to be. So this is where we can use also an example of the heat spreader just to get as much spreading over the housing and as much transfer to the ambient without having to invest in changing the mechanical toolings or changing my mechanical designs. It's just an internal hardware upgrade.
Yeah. And through this conversation, it's really apparent to me, you know, obviously that you two working within the same company, but really working within the same kind of parameters of thinking about that engineering design and how, you know, you can actually go from one area to the other, but, you know, bringing this conversation together, I think that's a really important thing to do, is to understand about the characteristics, not just in terms of one aspect of those characteristics, and in terms of the heat, in terms of the shielding, in terms of the EMI, for example. So I've really enjoyed this conversation. I just want to recap and thank you both for coming to talk to DesignSpark. And I think it's really important, obviously, you know, that you guys, the products that you're bringing out to the market are actually helping those engineers and taking into consideration those design challenges that engineers have. And I just want to, you know, is there anything else you want to talk about before we finish? Have you got any kind of application guides or any information on, you know, we talked about trends, but, you know, real world cases, case studies, if you like. Is there anything you want to just mention?
Just to make a short notice from my side is that shielding and thermal war sometimes are a little bit like, oh my God, where should I start? How do I face this? Is too much information. From our side, we always say, ask. Feel free to ask why. Why is behind this product? Why this one performs better? From shielding side, for example, we have an ABC of shielding, a new book that we have released, just explaining not from the product point of view, but also from the whole shielding point of view, what the customer has to take into account. Because sometimes it's simple that it's just understanding the principles, and obviously you can go really in detail about the specific topics, and yeah, you always can be hours talking about this, but the basics and the to start and to play with these products are not that difficult, and can make you to make a really smart choice when deciding how to design a PCB. And yeah, this is why we always encourage people and customers to ask, and designers, why it's working like that, or read our ABC for books, because what is behind the product, I think it's what truly matters. Not if you eventually use EMI patch or not, but why. Sometimes it's helpful to use a specific product from our portfolio.
Fantastic. Guys, thanks for your time today, and I hope we can have you on DesignSpark again real soon. So Sebastian, Maria, have a great day, and we'll talk soon.
Absolutely.
Thank you so much.
Thank you for having us.